One more transform that we should talk about is I want to talk about what happens when, instead of multiplying by an exponential, I want to think about what happens if we were to multiply by t. Okay, so if I were to take the Laplace transform, if I were to take the Laplace transform of t times f of t, what does that do to the Laplace transform? Remember that the Laplace transform of f, we're writing as capital F. So the Laplace transform of little f is capital F. Let's see. Let's think about all the things that can happen here. What I really want to do, just to explain this, is I'm going to work backwards a little bit. And I'm going to think about capital F of s being the Laplace transform of little f. So it's e to the negative st, f of t dt, integrated as t goes from 0 to infinity. And what I'm going to do is I'm going to differentiate both sides with respect to s, right? Both sides of this are functions of s. So I'm going to differentiate both sides with respect to s. And this is a completely unrigorous, it's a loosey-goosey proof here. But it turns out that what I'm going to do is I'm going to move the derivative inside the integral. Okay, this is a non-trivial step. It turns out in this case it's absolutely fine, but it's not obvious that it's fine. So what we're going to do is I'm going to take this and move through the parenthesis this derivative with respect to s. So we have e to the negative st, f of t dt. And the only reason I put e to the negative st in parentheses is that f of t is a constant with respect to s, so we don't have to do anything. And so this is going to turn out to be, if you differentiate e to the negative st, you're going to end up with, so if you differentiate e to the negative st with respect to s, you end up with a negative t, e to the negative st, f of t dt. In other words, you end up with negative integral from 0 to infinity e to the negative st, t f of t dt. And so what that means is that if we move this negative over to the other side, this means that the Laplace transform of t times f of t is equal to negative capital F prime of s. So multiplying inside the Laplace transform by t has the effect of taking the derivative of the Laplace transform and multiplying by -1. And so if you think about the consequences of that, just by applying this procedure over and over, if you think about the consequences, let's think about what would happen if we had t squared times f of t. And it turns out what we're going to do is this is going to be the Laplace transform of t times f of t. That's how I want to think about it. And what we're going to do is we're going to take the Laplace transform for t times f of t, which we just found. So that was negative f prime of s. And what we're going to do to that is we're going to differentiate that again. So we're going to differentiate this with respect to s and put another minus out front. And so the minuses combine to give us a plus, because we know we can bring minuses in and out of derivatives. And then we're going to take another derivative of f, and we end up with f double prime of s. And just one more, if I were to take t cubed times f of t, then what we're going to do is we're going to differentiate this quantity, f double prime of s, and put a minus in front of it. So if we differentiate again, we're going to get negative capital F. We're going to have 3 derivatives of that function evaluated at s. In other words, this is negative f. We're going to take 3 derivatives, and that's what we get. So in general, the Laplace transform of t to the n, f of t, means that you're going to have a -1 to the n out front, because for the odd powers of t, it's going to be, you're going to have a negative, and for the even powers of t, you're going to have a positive 1. So you get -1 to the n times the nth derivative of the Laplace transform, right, capital F. So that's what this rule is going to look like. And so let's just talk about some consequences here and some things that'll come up If I were to take, say, the Laplace transform of t times cosine of kt, what would happen? Well, we would end up with, we need to think about what's the Laplace transform of cosine of kt, and we're going to differentiate that with respect to s. So we're going to differentiate s over s squared plus k squared. And so when we do that, and I'll just leave this to you to check, and you really should check, but you end up with s squared minus k squared over s squared plus k squared squared. Likewise, if we do this for t sine of kt, and again, this means that you're going to apply this derivative and then a minus, okay? You're going to end up with 2sk over s squared plus k squared quantity squared. Again, just differentiating that k over s squared plus k squared quantity. Let's see, what else? A few other things that are helpful to know here, just because these look really nice. So these two functions are going to be very helpful for us. The way that they're going to be helpful is as follows. So it turns out that if you were to take the Laplace transform of, how do I want to say this? Let's say sine of kt. So sine of kt minus kt cosine of kt. And you just follow everything through, what you would end up with would be 2k cubed over the quantity s squared plus k squared squared. Okay, so that's what you would end up with there. And I know that that looks a little bit silly, but the reason why it's helpful is that, just to say this another way, if you were to take the inverse Laplace transform of 1 over s squared plus k squared squared, right, which is a term that conceivably would come up lots of times, especially if we're doing this partial fraction decomposition like we did for that second order differential equation. What we would get, though, would be 1 over 2k cubed times, in big parentheses, that quantity that we took the Laplace transform of, right, sine of kt, so sine of kt, minus kt times cosine of kt. Right? And so that is a very useful inverse Laplace transform to know. And likewise, if you were to take the inverse Laplace transform of s squared over the quantity s squared plus k squared squared, again, something that comes up a lot, you would end up with 1 over 2k times the quantity sine of kt plus kt cosine of kt. Okay, so that's what you would end up with there. That's how you use those, and those come up quite frequently when we're trying to find the inverse Laplace transforms. Okay, in certain applications. There's one more application of this that I just want to talk to you about, and that is so the next one I want to do is, let's take the Laplace transform of t times f prime of t, or x prime of t, or y prime of t, or whatever you want. What this means, remember, is that we're going to take the Laplace transform of f prime of t, which we said was s times capital F minus little f of 0. And that quantity, we're going to take the derivative with respect to s and put a negative in front. And so what I want to think about is, let's first just apply the derivative, and then we'll put the negative in front. So we're going to apply the product rule, and we're going to get the derivative of the first times the second plus the derivative of the second times the first. F of 0 is just a constant, so when we differentiate with respect to s, we get 0. So that's our formula. So we end up with negative s, f prime of s, minus f of s. Okay, so that is how that is going to work. And if I were to take the Laplace transform of t times f double prime of t, what we would do is we would think about what's our formula for the second derivative, and it turns out that that formula for the Laplace transform of the second derivative is going to be s squared, capital F of s, minus s times f of 0 minus f prime of 0, again, as discussed in a previous video. And so now, let's leave the minus on the outside here. We're going to take the derivative of the inside, again, do the product rule, so we get derivative of the first times the second, plus the derivative of the second times the first, minus, let's see, if we differentiate s, f of 0 with respect to s, we get f of 0, minus f prime of 0. It turns out that that part drops. And then I'll finally distribute in the minus sign, and we're going to end up with negative s squared, capital F prime of s, minus 2s f of s, plus f of 0. It turns out that's our formula for t times f double prime of t. Okay? And we are well on our way to all of the values, knowing all the values of this handout that I'm putting on Canvas. So we'll have a handout of all the Laplace transforms. In fact, maybe I'll next talk about that handout.